Saunderson. So James is a lecturer in the Department of Electrical and Computer System Engineering at Monash University in Melbourne. And before that, he was a PhD student at MIT and was a postdoctoral researcher at the University of Washington and postdoctoral scholar at Caltech. So please join me to welcome him to his talk on the lifting for simplicity, concise descriptions of convex sets. So please, James, this is your space.
Okay, great. Thank you very much. And thank you very much for the invitation to be part of this seminar series. So today my talk is very much on the optimization side of the variational analysis and optimization title for the seminar. And I think, it's much more on the mathematical programming end of things. And really today's talk is more of a survey and overview talk. So there's not many new results of mine in here really at all. But it's a talk based on a, okay, how do I do this? Oh, good. Based on a survey paper that I put together with Hamza Fawzi, Gouveia, Pablo Parrilo, and Reka Thomas that we put on the archive earlier this year. And so the idea is that it's a more high-level talk and hopefully relatively accessible to people with different levels of background and interest in the kinds of things that I'm going to be talking about. Okay, so what is this talk about? Well, it's about descriptions of convex sets that are useful for optimization and potentially for other things. And in particular, it's about giving descriptions that are efficient in some sense. And so we'll see that there's algorithmic implications, but we'll be much more interested in the mathematics of these concise descriptions than anything else. And our sort of starting point and our motivation is coming from already from linear programming. Okay, so what is linear programming? It's the minimization of a linear functional over a polyhedron. Okay, so here we've got, okay, this is probably familiar to everybody, I hope, but just to fix our terminology and particularly the way we're going to think about a polyhedron, we're going to think of it geometrically as the intersection of the non-negative orthant in some dimension, and the dimension of that orthant will correspond to the number of facets, typically, of this polyhedron. We'll think of it, this non-negative orthant intersecting with some affine space. Okay, so that's the way we want to think about polyhedrons. And so the number of facets is going to correspond to the sort of size of this non-negative orthant. Okay, so that's linear programming. But in practice, what are linear programs that we can solve in practice? Well, it's minimization of a linear function over a polyhedron that doesn't have too many facets. Okay, so in practice, if I have a polyhedron with exponentially many facets, this doesn't give me something that I can solve necessarily that easily in my computer. So we do care about the complexity of the description of the polyhedron. Okay, and so that's going to be a key theme in this talk, is thinking about the complexity of the description of the feasible region of something like a linear program, or more generally, convex optimization problems. Okay. So we've got an octagon on the previous slide. So here's a question. What, from the point of view of linear programming, what is the simplest description we could give of an octagon, of the humble regular octagon? Okay, so I mean, okay, if we go back to the picture, we can see that it's got eight facets, 8 faces here. It's got 8 vertices. So you might think that somehow, if I look at the number of facets, maybe I'll look at the number of facets or the number of vertices, and I see which is the smallest, perhaps this is the best description somehow from the point of view of linear programming. And that's very reasonable, but it turns out, not really to be true. So there's this very, basic, but not obvious until you've seen it, idea that you can potentially represent something like an octagon as the projection of a higher dimensional polyhedron that has fewer facets, that has somehow a simpler description complexity, if you like. And the key idea is that if Alex came to me and said, I want you to do linear programming over this octagon, right? And that was the problem I was tasked with. I could instead think about, doing linear programming over this higher dimensional polyhedron that projected onto my octagon. right? And if I could do linear programming efficiently over the higher dimensional thing, I can then do linear programming efficiently over the lower dimensional thing. And the reason is that if I take my cost function in the downstairs space, I can think of it as a cost function on the entire space and just optimize upstairs. Okay, and the projection of the solution upstairs will be a solution downstairs. So this kind of very simple observation, it turns out to be very powerful. And so just to give one example to show you that this is really non-trivial, it turns out that if you take, again, a very simple convex set in the plane, the regular 2 to the k gon, okay, it has 2 to the k facets. It turns out, and again, this is far from obvious, that there is a polyhedron or polytope, in fact, in a higher dimensional space that has only 2 k facets that projects onto that regular 2 to the k gon. Okay, so if you really want to do linear optimization over the regular 2 to the k gon, instead of writing all those 2 to the k facet inequalities, what you should do is instead write this much simpler object upstairs and do linear programming up there. Okay, so in particular, this shows you that you can have a sort of exponential reduction in complexity by doing this, by viewing your feasible region as the projection of a simpler feasible region upstairs. Okay. All right, so this is going to be one sort of example of a more general class or more general style of lifted representation. So what I want to do here is introduce some terminology, okay, that we're going to kind of generalize in a bit, and a particular way of thinking about these lifted representations. Okay, so on the left, I've got that same picture from before, a regular octagon downstairs, okay, and a polyhedron with 6 facets upstairs that projects down to it. Okay, and so we're going to think about the object downstairs as the primary object. That's what you gave me and said I want to optimize over this feasible region. We're going to talk about the upstairs object as being a lift of the downstairs object. So we'll talk about that as being a lift of P in this case. We'll use the symbol pi to indicate this projection. And so this will always be a linear projection, just to be clear, or just a linear map that has a non-trivial null space, typically. And the way we want to think about our polyhedron upstairs is we want to think about it as an affine slice of the non-negative orthant. So in particular, the intersection of the non-negative orthant with some affine space that I'm just going to call L, just as a kind of notation for it. Right, and we're going to have a notion of size for this lift because we're interested in the kind of complexity questions. So we'll say that P has a polyhedral lift of size M if I can write P as the projection of the intersection between the non-negative orthant in Rm and some affine space. Okay, and so now you can ask for any of your favorite polytopes. We're given a polytope P. What is the smallest lift that you can find of this polytope? Okay, and so this is like, now a question you could ask for any polytope, and in general, it's quite a non-trivial question to ask, or to answer at least. Okay, so that's going to be the key question somehow underlying the discussion when we focus our attention on polytopes and polyhedral lifts. All right, so that's enough of the sort of general picture. We've seen one example. I want to now present a couple more examples of polyhedral lifts of polytopes. So just everybody in polytope land, before we sort of take off and look at more general families of lifted representations. Okay. All right, so here's another sort of beautiful polytope called the polyhedron. This is a family of polytopes indexed by n. And what is this polytope? You take the vector 1, 2, up to n, okay? And you think about all different permutations of this, so you get n factorial different points. Then you take the convex hull. Okay, so this is a polytope. It has n factorial vertices, and it turns out that it has 2 to the n minus 2 facets. Okay, and if you think about it, all the vertices have the same sum. The sum of the coordinates is the same for all the vertices, so we can visualize this we can think about this as living in the affine space, you know, where the sum of the coordinates is whatever, you know, n choose 2 or n plus 1 choose 2 or something. And that's what this picture is on the bottom left. It says the permutahedron, all the permutations of 1, 2, 3, and 4, but living in that 3-dimensional space. Okay, so kind of beautiful polytope. But okay, it's got n factorial vertices, so lots of vertices, 2 to the n-ish facets. Does it have a small lifted representation? Okay, and the answer is yes, it has a couple of interesting ones. So one such representation, it comes from using the Birkhoff polytope as the polytope upstairs. So the Birkhoff polytope is the set of square n by n matrices with non-negative entries and row and column sums equal to 1. Okay, so this is often called the set of doubly stochastic matrices. It also turns out to be, and this is again a, you know, this Birkhoff von Neumann theorem, turns out to be the convex hull of all permutation matrices. Okay, so permutation matrices are the integer points in this polytope, and the Birkhoff polytope is exactly the convex hull of permutation matrices. Okay, and then from once you know that, it's perhaps not such a big surprise that you can write this permutahedron as a projection of the Birkhoff polytope. So what should the projection be? You should take a matrix upstairs in the Birkhoff polytope, an n by n matrix, and if you multiply it by the fixed vector 1, 2, 3 up to n, okay, that will give you all of the permutahedron exactly. All right, so this is an example of a lift of size n squared because this Birkhoff polytope has n squared facets. Right, and so for a long time, this was the smallest lift that we knew of the permutahedron. But then along came Michel Goemans. The papers from 2015, the results maybe from 2009. He sort of didn't publish it for a while. And he constructed this very, very interesting smaller lift of the permutahedron that has size n log n. Okay, and sort of, and there's this funny picture next to this theorem statement here. And all I want to say is that the construction of this lift is really interesting. I'm not going to tell you the details of it, but where the lift comes from is from a completely different construction of things coming from computer science. There are these things called sorting networks. And what sorting networks are is they're some kind of description of parallel input oblivious sorting algorithms. Okay, and you can think, why is sorting involved? It's because if you optimize a linear functional over the permutahedron, essentially what you do is sort the coordinates of the linear functional. Okay, the optimal solution is going to tell you how you would sort the coordinates of that linear functional. So somehow there's a connection between this and sorting. And it turns out that there's these sorting network things in computer science. And somehow there's a way you can associate with every edge of a sorting network a variable in a lifted representation of the permutahedron in such a way that you can show it projects back onto the permutahedron. So any new developments in constructing sorting networks immediately gives you better or different lifts of the permutahedron. So just I think the first instance in this talk of interesting connections to completely different fields from studying these kinds of questions. Okay, so that's an interesting example. We'll come back to this example a bit later in the talk. In particular, you could ask the question, so you know, on the previous slide, I said we're interested in finding perhaps the smallest lift of any given polytope. So this is a pretty small lift, looks like. I mean, but are there any smaller lifts of the permutahedron? Can you find a polytope upstairs with fewer than order n log n facets that projects onto the permutahedron? So we'll come back to that question later in the talk when we talk about ways to find obstructions to the existence of lifts, or to find lower bounds on the sides of the smallest lift. Okay. So let's go to another example, quite a different example. And I'm going to describe this only very, very, in a very cursory way. So another polyhedral cone this time, okay, that I'm going to call the horn cone. Right, so this is a polyhedral cone. It lives in R3n. And what it is what you do is you take your favorite triple of Hermitian n by n matrices that sum to 0. Okay, so imagine your favorite triple of Hermitian n by n matrices that sum up to 0. And now take the vector of eigenvalues of each of those. Okay, so the Hermitian matrices, so the eigenvalues are real. Okay, and you can order them. And so if you take the real ordered eigenvectors of A, eigenvalues, sorry, of A, of B, and of C, okay, that gives you 3n numbers in R3n. Okay, now look at all the possible triples you can get this way. It turns out, and it's, this has been known for a long time, that this is a polyhedral cone, which is already kind of a remarkable fact. It's completely not obvious this should be a polyhedral cone. And it was conjectured, I think, in the 50s by Horn. What he conjectured was an explicit sort of recipe for generating all of the facet-defining inequalities of this cone. So he had this kind of recursive procedure for generating all the facet-defining inequalities. The simplest such inequality is that if A plus B plus C equals 0 is an equality, then the trace of A plus the trace of B plus the trace of C should be 0. Okay, so that gives you an equality that these triples should satisfy. And then there's all kinds of interesting inequalities they should satisfy. So Horn had this conjecture about how these triples should be related. And it wasn't really until the late 90s when work of Cliacho and Knudsen and Tao really resolved this conjecture and showed that indeed Horn's recipe was correct for describing all the inequalities of this Horn cone. And it turns out there's a lot of them. There's certainly exponentially many inequalities for this Horn cone. Okay, but one of the really interesting things, from our perspective of lifts of convex sets that we're looking at here about the Knudsen-Tao work is that in fact the way their proof works is that they actually construct a lifted representation, a lift of this Horn cone. Okay, so they construct some other polyhedral cone that they call something to do with honeycombs. That's why there's a picture of a honeycomb here. And this turns out to have order n squared facets, and it projects onto this Horn cone. Okay, and the construction is really pretty explicit. Essentially have a variable for something like every edge in this diagram, and then sort of the inequalities come from somehow some kind of relationships that should be holding on this diagram. So it's very explicit and kind of beautiful, but the proof is really tricky. Okay, what does this allow you to do? Well, certainly it allows you now to do linear programming over this Horn cone if you ever wanted to do that. But it also kind of leads to other interesting things. So some of the observations in the Knudsen-Tao paper is that in fact, certain like decision problems related to the representation theory of GLN. So like whether when you look at tensor products of certain representations of GLN, whether they have a copy of the trivial representation inside them, you can answer some of these things algorithmically by actually doing linear programming over this Horn cone in a certain setup. So there's kind of interesting applications to things very far from optimization, if you like. Okay, that's just a kind of remarkable but interesting polyhedral lift coming really from things far away from, I think, what I certainly usually think about. Okay, so let's now go bigger picture than polyhedral, than polytopes and polyhedral lifts. Okay, so what we want to think about here is a kind of generalization of that story, where what we do is we again start with a convex set downstairs. So that's the thing we perhaps want to optimize over. And what we'd like to do is construct again a lifted representation of that set that's somehow easier or nicer from a point of view of, say, optimization. And in particular, what we're going to look at is situations where this lifted set is again an affine slice of some closed convex cone K. Okay, so often what we do is we think about fixing a cone K, for example, and we'll discuss this example on the next slide, a cone of, say, some m by m positive semi-definite matrices, and think about which sets C have a lifted representation using that particular cone. Okay, and again, we're going to say that C has a K lift, where K is the cone, C is the object downstairs, means the same as I can write C in this form as the projection of the intersection of my fixed cone K with some affine space. So the two things you get to play with here are the affine space L and the projection pi. And then in the kind of fundamental question that you can play over and over again for your favorite sets is, okay, given a convex set C downstairs and a cone K that I know how to optimize over, you can ask, does C have a K lift? Okay, it turns out that we know lots of interesting examples. But also there's been developing a theory of understanding, of trying to characterize this question, and in particular trying to also answer when does C not have a K-lift? So when can I not just construct a lift, that gives me one side of things, but also convince you that it's not possible to construct a lift. Okay, and so later in the talk, I want to discuss briefly sort of some of the ingredients that go into trying to answer these questions, and some of the little bits of progress here and there that the community has made and try to answer some of these questions. Okay. All right, and so we're not going to spend really in this talk, and in our survey paper also, we don't spend much time at this level of generality. So mostly we're going to focus on a kind of a very specific case of the cone, and it's the case that comes from semi-definite programming. Okay, so again, for those not familiar, what is semi-definite programming? It's really an analog of linear programming where you replace the non-negative orthant with the positive semi-definite cone. Okay, so you need to minimize the linear functional over, again, an affine slice here. This is defining my affine space of the positive semi-definite cone. So I will sometimes use this curly inequality to indicate that this thing on the left here, which is an m by m symmetric matrix, that it's positive semi-definite. So all of its eigenvalues are non-negative. So some terminology we're going to use in the rest of the talk. We're going to use the term spectrahedron for an affine slice of some PSD cone of some size, just like the term polyhedron for an affine slice of the non-negative orthant of some size. And then if we want to specify the size, we'll say a spectrahedron of size m. Okay, to be specific that we mean an affine slice of m by m PSD matrices. And again, what's going to turn out to be the case, at least for this discussion, is that we'll use the size of the matrices, this parameter m, as really our notion of complexity of the description. It's a kind of coarse notion of complexity. We could certainly have much more refined notions. But for our purposes today, let's focus on this dimension of the matrices involved in this SDP, in this semi-definite program, as being our proxy for complexity. Right, and just to show you that you really get things from semi-definite programming that are different from polyhedra. You certainly can have all polyhedra in this case, but if you look at different possible feasible regions for semi-definite programs, you can get smooth things like the set on the bottom left. You can get sets with all kinds of interesting singularities and so on. This is just spectrahedra in R3, so it's pretty hard to imagine how crazy and interesting these sets are in general. Okay, so this is quite a bit more expressive kind of extension of linear programming. And so now if we look at our lifting question, we can focus, and we will focus for much of the talk on spectrahedral lifts of convex sets. So again, you give me a convex set, and I want to ask, can I construct a spectrahedral lift? That is, can I find a PSD cone in some dimension and an affine space, so that if I take the intersection of the PSD cone and the affine space, and I project it by some projection, I get the convex set that I want. And again, just to sort of see that some interesting and weird things can happen, if you take this very nice convex set, this three-dimensional spectrahedron on the top left, this is what we often call the elliptope. It's a convex body that appears particularly a lot in semi-definite programming relaxations of combinatorial optimization problems like maxcut, for example. It turns out that if you take this thing and you really project it in the right direction, you really get a polytope. So it's also interesting to ask for polytopes, not just about their about polyhedral lifts, but you can also ask about spectrahedral lifts of polytopes. Okay, you could consider both of these. But if you take the same convex body and you project it in a different direction, you will get a different convex body downstairs. It's no longer a polytope, right? It's kind of a puffy triangle, has some curvy edges, so it's definitely not a polytope. All right, so I'm just trying to give the impression that you can already get interesting different things even in this very simple scenario. One important point to note that's really different between the polyhedral case and this spectrahedral setting is the following. In the polyhedral setting, If you take, you know, a polyhedron upstairs and you project it, you're going to again get a polyhedron. All right, so that somehow this is, if you like, a consequence of, say, Fourier multiplication elimination tells you that, you know, you remain a polyhedron downstairs. Okay, so you don't sort of enlarge the class of possible convex bodies, you enlarge the complexity, but not the sort of class. This is not the case for spectrahedra. So if you take a spectrahedron upstairs, that is an intersection between the PSD cone and an affine space, okay, and you project it into some lower dimensional space, you can get convex bodies that are not spectrahedra anymore. Okay, and one of the sort of easiest ways to see this is it's true, not super hard to show, that all of the faces of spectrahedra are exposed. Okay, but it's fairly easy to construct projections of spectrahedra that do not have exposed faces. In fact, we might see one later in the talk. Okay, so this is already shows you that somehow you can really enrich the class of convex bodies you can deal with by thinking about projections of spectrahedra. Okay, so again, we have the same kinds of questions. Given a convex set C, does it have a spectrahedral lift of some size? And if so, find the smallest spectrahedral lift. Okay, so these are again going to be the overarching type of questions that we might want to consider in this space. And again, if you know, if I can find such a spectrahedral lift, that allows me then to do optimization over this set C by using semi-definite programming. All right, so let's look at you know, a couple of examples, and this is kind of, you know, if you like, an example that is behind a lot of the constructions, a lot of the ways to construct spectrahedral lifts that we'll discuss a little bit later in the talk. Okay. All right, so this first example we're going to look at is, we first consider the set of non-negative polynomials, so multivariate polynomials. Okay, so in n variables of degree 2D that are globally non-negative. So no matter what you plug in, you get a non-negative number out. Okay, so this is some convex cone. Turns out the closed convex cone are in the, you know, in the space of polynomials in n variables of degree 2D. Okay, so some convex cone. Turns out this is quite a difficult convex cone to deal with, and in general, it's hard in the sort of computational complexity sense, at the very least, to check non-negativity of if you just give me an arbitrary multivariate polynomial, it's going to be tricky algorithmically for me to check non-negativity. But it's something I can do, you know, in general with something like quantifier elimination, but to do this efficiently is not expected to be possible. On the other hand, and there is a convex cone, another convex cone that is in some sense related to the cone of non-negative polynomials, and that is the cone of sums of squares. Okay, so I'm using this notation on this slide, and the next one, SOS for sums of squares. Again, this is some collection of polynomials in n variables of degree 2D, and sums of squares are going to be polynomials that you can write as a sum of squares of other polynomials. Okay, so perhaps the easiest definition there is. Right, and so clearly, if I can write a polynomial as a sum of squares, then it's non-negative. So the sum of squares cone is inside the cone of non-negative polynomials in general. And from our perspective of this talk, the reason that the sum of squares cone is particularly interesting is that the sum of squares cone has a spectrahedral lift. Okay, so I'm not going to say what it is right now. If you've seen it before, you know what it is. It's not very complicated, but you know, just for the sake of brevity, I won't spell it out in detail. But it has a spectrahedral lift of size n plus d choose d. So in particular, if the dimension or the degree is fixed, this is a polynomial size spectrahedral lift of the sum of squares cone. And so if you want to do optimization over the sum of squares cone, or over, you know, slices of the sum of squares cone and so on, which turns out to be very useful and very flexible and used in many, many areas, you can rewrite those as semi-definite programs because of this lifted representation we have of the sum of squares cone. The other consequence is that there's a, you know, classical result due to Hilbert that says that the sum of squares cone equals the cone of non-negative polynomials in a few very special cases. So in the univariate case, okay, so any univariate non-negative polynomial is a sum of squares. In the degree 2 case, sorry, that should say d equals 1, not d equals 2. This is a typo. So in the degree 2 case, where any non-negative quadratic is a sum of squares, okay, it's relatively easy to see this. And then there's just one exceptional special case where of polynomials in two variables of degree 4, okay, where non-negativity equals sums of squares. So in these cases, not just the sum of squares conal, but equivalently, the non-negative polynomial cone has a spectrahedral lift of a particular size. And so this is quite useful, particularly in the n=1 case, in the univariate case. So essentially, I mean, really most optimization problems involving univariate polynomials, you can, if you want to, reformulate them as semi-definite programs. It's not always the best thing to do, but it can be a very, surprising and useful thing to do in some cases. All right, so this is already an interesting spectrahedral lift. One sort of very recent and very kind of important result that we'll touch back on a little bit later is this result of Klaus Scheiderer from a couple of years ago that says, in fact, in every other case, so apart from these cases, n=1, d=1, or n 2d = 2, 4, it's not just that the cone of non-negative polynomials has a really complicated, difficult spectrahedral lift. It just has no spectrahedral lift whatsoever. So there's no finite sized PSD cone you can slice and project to give the cone of non-negative polynomials in n variables degree 2d, except in these particular cases where we know a lift already. Okay. So building on this, and this is partly because some people in this community have spent some time thinking about these SOS convex polynomials, I wanted to give this other example of a spectrahedral lift that I find quite interesting. Okay, so firstly, what are SOS convex polynomials? And then what is this lift that I want to tell you about? Okay, so let's start with convex polynomials. So there's many different definitions of convexity. If I look at the first order characterization of convexity and I focus on polynomials, what it says is that this expression here that I'm writing d sub p of xy, calling it this because it's often called the Bregman divergence associated with the polynomial. So if I have a polynomial p is convex, if and only if this polynomial, it's now in 2n variables of degree 2d, okay, if p was of degree 2d, if and only if this polynomial in 2n variables is globally non-negative, right? This is just the first order characterization of convexity. It just says, if you like, that the linear approximation at a point is a lower bound globally. Okay. So maybe about 10 years ago, this definition alternative or this special class of convex polynomials was introduced called SOS convex polynomials. Okay, and so what are these? These are polynomials of degree 2d, where this Bregman divergence is not just non-negative, but it's a sum of squares. So we have some kind of concrete certificate that this Bregman divergence is non-negative, and so a kind of concrete certificate that P is a convex polynomial. Again, in general, it's known that checking convexity of polynomials already in degree 4 is NP hard, right? But checking convexity of, or checking SOS convexity, which is a sufficient condition, is something that, again, we can do by semi-definite programming, by a semi-definite programming feasibility problem. Right? So that's one interesting thing. This effectively gives us, we could extract from this expression a spectrahedral lift of the set of SOS convex polynomials in the language of today's talk. Another little result I want to just share that's very related is, it turns out that for SOS convex polynomials, we can give a nice spectrahedral lift of their epigraph. Okay, so what's the epigraph? This is the set of points in n+1 dimensions where the polynomial, in this case, is less than or equal to that last scalar coordinate. Okay? This is the epigraph. Epigraphs are of particular interest, I think, in sort of optimization in the conic point of view, because we can always, well, maybe I won't say that. I think everyone in this audience is probably pretty familiar with this idea of viewing a convex function in terms of this convex set. So what's the result? It turns out that you can give an explicit spectrahedral lift of the epigraph of a SOS convex polynomial, and it's really just exactly this. So you look at the points xt, such that t minus blah, blah, blah stuff is a sum of squares. Now this expression, I'm only thinking of as a polynomial in y, so it's a polynomial of degree 2d in y, if p had degree 2d. and it's linear in T and X. So this is really saying that the epigraph of an SOS convex polynomial is a slice of the sum of squares cone. And because the sum of squares cone has a spectrahedral lift, it gives you a spectrahedral lift of this epigraph. Right, and my picture here is just the one sub-level set of the intersection of the one sub-level sets of two convex polynomials. It really is a convex set, just it's a bit mind-blowing. Okay. So this is sort of the end of the potpourri of random examples part of the talk. So what we've seen are some examples of polyhedral lifts. We've seen a couple of examples of spectrahedral lifts, these ones coming from sums of squares, but there's many others. I just wanted to focus on these today. Now what I want to do for kind of the rest of the talk is introduce give you the flavor of some of the tools we use to try to understand these questions both about, how do I construct lifts somewhat systematically. I haven't given you any systematic procedures so far to construct these, just told you that they come from somewhere. But also on the other hand, how do we get systematic tools to try to prove that it's not possible to construct lifts, that we shouldn't try harder to find better lifts of certain objects, that we've found the good lift and we're done and we should stop and move on with life. Okay, and so the first object I'm going to introduce here that helps us understand these questions is a thing called the slack matrix, or more generally, when we look beyond polytopes, we'll call it the slack operator. Okay, so it's a very simple object, but I'm just introduce it a little bit slowly so that we all are on the same page. So imagine I have a polyhedron, but I'm going to focus on polytopes with the origin in the interior, just to make life a bit simpler. So then I can write this polytope here. I can sort of normalize all the facet inequalities so that I have one on one side. Okay, and I'm going to be focusing in the next couple of slides on polytopes with V vertices and F facets, just for notation. Okay, so associated with this polytope, what I'm going to do is build an entry-wise non-negative matrix. Okay, and this matrix I'm going to call the slack matrix. It's indexed by vertices on one side and facets on the other side. And the ij entry is just 1 minus, it's really just the slack in that facet defining inequality evaluated at the vertex. Right, so I just plug in the jth facet and the ith vertex. 1 minus this quantity should be non-negative because the vertex is in the polytope, so it must satisfy this inequality. Okay, so I can do this for every facet, for every vertex and every facet. Okay, and I'll get a potentially huge entry-wise non-negative matrix. And so, for example, if I did this for the regular hexagon, what I'll get is in fact this circulant type matrix. Because if I think about, say, a facet like so, the vertices that lie on this facet will get zeros in here. The next level of vertices will say, take value 1, that will be this one and this one, if I order the vertices cyclically around here. And then these other vertices will have value 2 for this linear functional that defines this facet. Okay, so this is just a concrete example. So why are these slack matrices interesting? Well, they give us a way to, in fact, characterize the existence of polyhedral lifts, right? So, so it's really interesting way to really understand polyhedral lifts by looking at this entry-wise non-negative matrix, and in particular by looking at certain factorizations of this matrix. Okay, so to describe this, I want to remind us the definition of the dual cone. So if I have a convex cone K, the dual cone for me is going to be the set of linear functionals that take non-negative values on that cone. Okay, and then we're going to define this idea of a K factorization of the slack matrix, say. And what it is that it's really going to be about having two maps. One is a map from the vertices of the polytope P into the cone K. The other is going to be a second map from the facets, okay, so the facet normals, essentially, well, actually no, just from the facets to the dual cone. And what I want these mappings to do is I want it to be that the slack matrix, the ij entry, is going to be the inner product of the bj coming from where the facet landed in the dual cone, and ai coming from where the vertex landed in the cone. in particular, if I could construct such a factorization, such a description of my slack operator, this implies that this sort of certifies that all these entries are non-negative, right? Because if I take the inner product of AI, which is in the cone, and BJ, which is in the dual cone, then by definition, this should be a non-negative quantity. Okay, so this is somehow a little bit stronger than saying that the slack matrix is entry-wise non-negative. It's saying that in fact, I can certify those inequalities using this cone K and its duality and its dual cone. Okay, so in particular for this slide, we're going to be interested in factorization through the non-negative orthant. And because the non-negative orthant is self-dual, okay, what I'm really saying in this equation here, I'm really saying that the slack matrix has a non-negative factorization. So I can factor it as the product of two matrices, one coming from the entries of A, the A's, one from the B's. We'll see an example on the next slide, where all of the entries of those matrices are entry-wise non-negative. Okay, and what Yannakakis showed, in the early 90s is that, the slack matrix has an orthant factorization in the size M orthant, if and only if a polyhedron or a polytope has a polyhedral lift of size M. Okay, so somehow understanding these factorization questions, this algebraic type question, is exactly equivalent to understanding this geometric question of taking an orthant, slicing it with some affine space, and then projecting onto some lower dimensional space. Okay. A little bit, interesting backstory with this paper of Yannakakis. So this is sometimes called people view this as one of the best reviews ever written. So essentially Yannakakis was sick and tired of crackpots sending him proofs that P equals NP that involved writing extremely complicated lifted representations of the traveling salesman polytope of polynomial size. So he was like, I really need to have a slick way or a way to show that these don't work. And so he essentially built this theory of this factorization theory and proved some other results about these combinatorial polytopes from it, essentially as a way to refute the failed attempts at proving P equals NP by giving polynomial sized lifted representations of sort of difficult combinatorial polytopes. So I wish all my reviews were that substantial. Okay, so just to give you a concrete example, if we go back to our hexagon case, we have the slack matrix here, and it turns out you can write this non-negative factorization. So what's going on here is that this is the, the image of, these are the A's in the factorization map, one for each vertex. Okay, they're non-negative vectors, they're in R5, and the same, these columns are the B vectors in the factorization. And the consequence of the existence of this factorization is that the regular hexagon has a size 5 polyhedral lift. So it has a, okay, yes. And we should be able to count the facets here. Okay, did I screw up? Okay, I'm having trouble counting, but this regular hexagon should have a lift. Okay, I've got the wrong picture in here, that's what's wrong. So I've drawn an octagon, so this is why it doesn't have an R5 lift. But if I had a hexagon here, there is in fact, and I'll leave it to you for homework, has a lifted representation with 5 facets. Okay, so what's interesting is that not only can you, conclude that from this factorization, but you can in fact computationally extract the lift directly from the factorization, and vice versa. If you have a lift, you can construct a factorization explicitly. So this is all quite constructive. Okay, so that was for the polyhedral case, and it turns out there's a nice generalization of this to the much more general story of general cone lifts. Okay, so back to our fundamental question, given a convex body and a closed convex cone, when does C have a K-lift, have a representation of this form? So it turns out there's a generalization of this slack matrix called the slack operator. We'll see an example on the next slide. And if this cone is nice, and I mean nice in the sense of facially dual complete, then you have an equivalence that says the downstairs object has a K-lift, if and only if some slack operator object associated with the downstairs convex body has a K factorization. So it has some kind of factorization using this convex cone K. If you don't have this technical assumption here, you get one direction but need to make you need essentially a constraint qualification to make this work. Okay, so this both generalizes Yannakakis' theorem perfectly to this general setting, but it also, and we'll see this in the next few slides, gives us a systematic way to find both constructions of lifts and obstructions to the existence of lifts. Okay, I'm going to skip this example in the interest of time. Maybe if I share the slides later, you can look through it, but it gives a sort of explicit example of a convex set here, okay, and it's polar, all right? Explicit sort of parameterizations of the extreme points, okay? It describes the slack operator, and it gives a sort of explicit factorization. Okay, what is a factorization? In this case, you should map every extreme point to a 3x3 PSD matrix, every extreme point of the polar to a 3x3 PSD matrix, okay, in such a way that the slack operator is exactly factorized in this way, right? And so you can check the details and see that this really works on a concrete example. And this tells us that this, this cubic curve has a size 3 spectrahedral lift. Okay, and in principle, you can extract that lift from these matrices. All right, so how do I go about constructing spectrahedral lifts? So it turns out you can look at this factorization theorem and reinterpret it in the following way that's quite useful from a constructive point of view. So what this says is that if you have some set and you're interested in the convex hull of that set, you're interested in giving a spectrahedral lift of that, the convex hull of some set X, okay? That this has a spectrahedral lift if and only if you can write any valid inequality essentially as a sum of squares. And so what do I mean by this? Let me say a little bit more slowly. So what I mean is that I should be able to find a subspace, an m-dimensional subspace of functions on these points X, which we often think of as the extreme points of our set, such that any linear inequality that should be true for this set, so any linear inequality from the polar, can be, if I restrict to my set X, it's a sum of squares of functions from this subspace. Okay, so somehow there's an intimate connection between spectrahedral lifts and sums of squares once I work with the right set of functions, essentially. And so what this tells me is that if I want to construct lifts, sort of what I need to do is construct subspaces of functions on the extreme points from which I take sums of squares and try to certify all the linear inequalities that are valid using sums of squares from this subspace. Right? And so again, to give a concrete example, this spectrahedral lift of the square that we showed right at the start of the talk, you can really choose all the data in this construction. You can choose a 3-dimensional subspace of functions, okay? Essentially just the constant and the coordinate functions. And if you restrict to the vertices of this square, which is just the ±1 coordinates, it turns out that the facet inequalities, which are these, okay, can be written as, in fact, they are essentially squares once you restrict to ±1 valued points. Okay, so this, and from this kind of observation, you can extract this explicit spectrahedral lift. Okay, and because my dimension of my subspace of functions had dimension 3, I get a lift of size 3. Okay, so somehow, once you can validate all, verify all these inequalities are sums of squares from your subspace of functions, that's the hard bit, then you get an explicit lift out of this. Okay. The question is, of course, how do I choose my functions? And one natural choice is to choose polynomial functions of some degree. This is a natural choice if your set X is somehow algebraic, like an algebraic variety. But in fact, this doesn't always work. So this is an example here, this piriform curve of an algebraic variety, where if you want to describe the convex hull using this kind of approach to give a spectrahedral lift of the convex hull, if you use just polynomial functions in the previous construction, you will never be able to describe the convex hull that way. But you can, in fact, if you use rational functions, you can make it work. Okay. So it turns out that what's true is that if you have this algebraic set, and it does have a spectrahedral lift, then it's not enough to choose polynomial functions in this construction, but it is enough to choose semi-algebraic functions. So there is some control over these functions that appear. Okay. So that's all I want to say on the constructive side in general. I just want to give you a sort of a flavor of what goes on. In particular, there's a strong connection between spectrahedral lifts and sort of essentially sum of squares certificates of the facet inequalities, or the defining inequalities, if you like. I want to spend the next couple of slides talking about obstructions. So what do I mean? I mean, is how do we answer these questions in the negative? So if you give me a convex set C and you give me a convex cone K, how do I convince you that there's no possible way to give a K lift of C? Okay, so I just want to touch on, again, a couple of ideas out there in the literature on this that are quite different and sort of interesting to me. And so again, because we have this characterization, this characterization of lifted representations in terms of K factorizations, cone factorizations, instead of looking for obstructions to lifts, I can equivalently look for obstructions to factorization. And often instead of looking at all the information in the slack operator, often I'll do something quite coarse. I might just look, for example, at the I meant to say not one, the zero non-zero pattern of slack information. And one thing that turns out to be the case is if you look at where the slack matrix is 0 and non-zero, that essentially tells you the incidences between extreme points and faces. Okay, so somehow you can, if you want to look at this coarse information from the slack matrix, you're essentially looking at the facial structure of your convex set. And so once you look from this point of view, it's relatively easy to show that if C has a lifted representation using K, that induces an embedding of the face lattice, or in particular just the poset as a poset, induces an embedding of the partially ordered set of faces of C into the partially ordered set of faces of K. And so again, this is just some picture that is illustrating that embedding. So we've got some convex set down here, 2, 3, 4, with 8 vertices and 8 facets. 8 vertices, 8 edges, 1 full dimensional face, and the empty face. Okay, this other polyhedron projects onto it, and this gives some embedding into its face lattice, and its face lattice embeds into, because it has 6 facets, sorry, it embeds into the face lattice of the non-negative orthant in R6, which is this bigger guy. Okay, so somehow this really happens. And you can then use this to find obstructions. So one of the simplest ones you can do is you can say, well, if the face lattice of the downstairs thing has to embed into the face lattice upstairs, every vertex downstairs has to land on a face of the non-negative orthant upstairs. And from this, you can deduce the following kind of lower bound on the size of lifts. Okay, so again, a result of Goemon's that if you have a polytope with V vertices, then and you want to give a lifted representation, then you need at least log 2 of V number of facets upstairs. And this tells us that the lift of the regular 2 to the n gon that we saw at the start is essentially optimal. It also tells us that the lift of the permutahedron that Goemon's found is essentially optimal because log of n factorial is roughly n log n. So that's one very simple obstruction you can get from this face-centric point of view. Another is that you can look at things like the longest chain of faces downstairs and the longest chain of faces upstairs, and this can allow you to deduce simple things. Like, for example, by looking at chains of faces, you can tell that this dual of that cubic curve cannot possibly have a lifted representation where the cone upstairs is a nice smooth cone. There needs to be some kind of singularities upstairs in the cone to make this work. So you can get kind of surprisingly powerful seeming conclusions from pretty simple arguments this way. I'm going to go pretty briefly here. I just want to say that, looking at the face structure is one thing, but once we start to look at these these particular spectrahedral lifts, we can try to look also for more algebraic conditions that should be satisfied if something has a lift. Okay, so that's really what this slide is about, that you can look at some algebraic properties of the convex set downstairs and potentially conclude either lower bounds on the size of spectrahedral lifts, or even conclude that sort of if the set downstairs is not semi-algebraic, that you couldn't possibly have had a spectrahedral lift. So the last is getting pretty close to the end now. I just want to give a quick overview of some of the most interesting results that have happened on the negative side, and a few open questions that I particularly like. Okay, so some of the sort of obstruction style results are the following. So I should maybe preface this by saying that there's been quite a lot of activity in the last, I would say, 5 to 10 years, probably 10 years, on this kind of obstruction side of this story. Mostly initially focused on the polyhedral setting, and really a lot of interest from theoretical computer science people. And I think much more recently on trying to find obstructions from spectrahedral lifts, which is quite a bit harder. And sort of some of the highlights have been the following: that certain combinatorial polytopes, like the traveling salesman polytope and the cut polytope, you can prove that they need exponential size lifts, which is perhaps not surprising, since optimization over these things should be kind of difficult. A really interesting example is the case of the matching polytope. So linear optimization over the matching polytope. Again, this is some polytope that's related to perfect matchings in a graph. So linear optimization over this polytope can be done in polynomial time using the Blossom algorithm of Edmonds. But in fact, if you want to give, but there's no polynomial size lifted representation like this. So somehow it tells you that there are linear programs that, there's linear programming problems, that it's not the only way to get efficient methods is by doing lifted representations. There's some, efficient algorithms that are not captured by this approach. This result of Scheider that we've already seen, that non-negative polynomials in 2 variables of degree 6 has no spectrahedral lifts. This is quite an important result. Was the first case where we had a convex semi-algebraic set that was known not to have a spectrahedral lift. And also kind of the spectrahedral analog of these results about combinatorial polytopes. So again, very recent results, and quite difficult results, at least the current proofs are quite complex. All right, so sort of getting near the end, I've discussed, I think, this idea of trying to give concise descriptions of convex sets by looking at them as projections of simpler objects upstairs. We've seen a whole bunch of different examples, both on the polyhedral side, some really classical polytopes, really non-obvious constructions, and this much more modern study of spectrahedral lifted representations. There's lots of interesting work to do in this area. I think hopefully you can see that it connects to all kinds of different areas of mathematics. So it's very stimulating, interesting to work on. And some of my favorite problems, I think all of these are quite hard. But I think give you a sense of some of the interesting problems in the area. So we discussed that for polytopes, you could consider polyhedral lifts, but you could also consider spectrahedral lifts. And spectrahedral lifts are it's a more powerful kind of language. So you could expect that spectrahedral lifts would be, in general, could be smaller than polyhedral lifts. So we could ask, can we find a family of polytopes where, there's a big gap between the size of the smallest polyhedral lift and the smallest spectrahedral lift. And kind of the biggest gap we know at the moment is sort of not that big, actually. Right, so it's growing, but it's not sort of that impressive. We'd sort of imagine there might be cases where there's an exponential gap, but we don't know any such examples. So building on Scheider's work, we could ask, what's the smallest dimension in which there's a convex semi-algebraic set that does not have a spectrahedral lift? We know that this dimension must be at least 3 because it's also been shown that every 2-dimensional convex semi-algebraic set does have a spectrahedral lift, which is also quite a difficult, interesting result. And then we've seen that the matching polytope, even though you can optimize over it in polynomial time, doesn't have a polynomial size linear programming lift or polyhedral lift, but doesn't have a polynomial size spectrahedral lift. So this is a open question, also possibly quite difficult, but very, very interesting. I think we'd learn a lot from answering or making progress on any questions of this type. All right, so I wrap up there. I've probably gone over time a bit. Thank you very much. Again, most of this was survey and overview of the area. If you're interested and you want to see more pretty pictures and so on, we have this survey paper that's on the archive that you can read more about these examples and get much more into the details of some of the things I've talked about today. Thanks very much.
So thank James for your beautiful talk. Did anybody have a questions, so please type in the chat section that we will give ask to our speaker. So can I have my question first to James?
Mm-hmm.
Okay. So given a polytopes and I have a Fay lattice, so a facial structure, which means that the Fay lattice with the inclusion order, right? So given a Fay lattice, can I say that, I mean, there are two polytopes are equivalent to each other if they have the same Fay lattice? Can I have two polytopes have the same equivalent to each other but have a different lift? And
yes, yes, that's a great question. So I guess the question here is, so this lifting stuff is, really the notion of equivalence we think of here is, just affine isomorphism. But if you ask, about, polytopes up to combinatorial structure, can you have, two polytopes with the same combinatorial structure, but for example, one has a lifted representation with 7 facets,
mm-hmm.
the other show needs at least, 17 facets. And yes, there are examples that show that these things can be quite different. Like for example, I think a good case is things like these regular polygons, the difference between regular polygons and sort of general polygons have the same combinatorial structure, but the regularity really helps, some special things happen in constructing these things.
So apart from your characterizations and in the very end of the slide, there is some properties say about the longest path between the face.
Mm-hmm.
So, but I think as long as this is a convex body, it should be infinite, right? I mean, the chain of faces.
Chains, so not necessarily. So anti-chains perhaps, but the chain. So for example, in this case of this one here, if you can see, there's the empty face. Then you would have, I mean, potentially here's a chain. You have empty face, an extreme point here, and then this full dimensional face. Or you've also got the empty face, this extreme point here, this, one-dimensional face, and then the full-dimensional face. So that's kind of the longest chain you can have here.
Okay, the chain face means that you go higher dimensions, not just.
Yes, so it is a kind of a theorem that the dimension must increase along chains.
Okay, I see. Okay, thanks.
Yep.
So we have another questions from channels. Can you read your questions to the speaker, or I will read your question?
Yeah, we'll try. So the question is, if you have, you said that spectrahedra project down and they need not be spectrahedra. So the question is, I mean, just like if you want to take square roots, it's a good idea to look at the completion of R. So maybe there's some kind of completion here too that would make that possible. I mean, it would be computationally probably not very useful, but theoretically could be interesting.
Absolutely, that's a very interesting point, and I certainly don't have any idea what that would look like. But I mean, certainly if you go to a big enough space, then I can just write all the. I can just write all the extreme points of the polar, and these are just linear inequalities. So somehow we want something non-trivial between that infinitely many linear inequalities and, that can capture things like non-exposed faces and so on. So yeah, I don't know. Very interesting question.
Okay, thank you. Is there any other questions for James?
Thank you very much, James. Very interesting presentation.
Good. Thanks, Alex. Well, thank you everyone very much for attending. I mean, it's really great to see so many people here. So.
Can you read the chat or?
Yes, I'm seeing the chat, and
okay.
Yes, thank you everybody who's.
Yeah, thanks, James. So I think we probably don't have any more questions for you. Then if you have some follow-up follow-up questions and you contact you in person. So I will close the section today. So next week we also have a seminars. So so looking forward to see you all next week. Thank you.
Thanks.
Thank James. Hey everyone.
Thank you. Bye-bye.